and welcome to today's webinar. The topic of the week is hydrogen technology and thermal analysis. Before we go through the slides, just a hint for those who just recently joined. If you have questions, please use the chat function of the platform and write and type your questions in there. We will discuss them after the presentation. In case you need more information or you have very specific questions, drop us a mail or contact us by phone or by mail or by website, by social media, whatever you prefer. And then we can discuss that afterwards. In case you have connection issues or issues with sound and video, don't worry, there will be a video available of the webinar that you can request by mail as well, and then you can watch it whenever you want again. So back to the topic. Today's topic is hydrogen technologies and hydrogen and thermal analysis. Before I start, I want to introduce myself. For those who do not know me, my name is Sebastian Seid. I'm the head of laboratory here in Germany at the Linzheis headquarters. I'm a chemist coming from organic chemistry, doing catalysis and doing calorimetry here at Linzheis since 2013. In case you want to have a test measurement, in case you want to have customization of instruments, or you have questions about a certain application, you can get in touch with me directly, or you can just drop a mail to Linzheis anyways. I also want to introduce the company for those who do not know the company yet. The Linzheis Messgeräte is a manufacturer of thermal analyzers and was founded in 1956 here in Selb, where we are still located, by Dr. Maximilian Linzheis, the guy on the top left picture. Meanwhile, his son, Mr. Klaus Linzheis, is our owner, and the sons of Klaus Linzheis, Mr. Florian Linzheis, and his brother, Dr. Vincent Linzheis, are our CEOs and doing the operational daily business. We have about 100 employees here in Germany, and we have subsidiaries and facilities in the US, India, and China, where we have offices for distributing, maintenance, repair, and field service to be available all over the globe. In all the other countries, we have distributors who are representing us since many, many years to be available really in every corner of the world. If you want to have a Linzheis instrument, there is somebody who can help you to create connection with us, and who can repair your instruments, who can maintenance them, and can help you by installation. Our main business areas, as said, is mainly the manufacturing of thermal analysis instruments and instruments for thermal conductivity, as well as thermoelectrics. Linzheis started up also with data loggers, which we do nowadays no more. That was sold to another company, but in the past we also did this XY data loggers, which was a quite good product. Nowadays, as said, we are focusing on thermal analysis instruments and, of course, lab service measurements. Here on the picture down here, you can see one of our labs, how they look like. All the instruments we offer are also available in one of our labs, and you can send us samples for service testing if you want. The product range we manufacture and the product range we are talking about can be seen on the slide. Usually, I would structure a talk like this. If it would be about one instrument or one instrument series, I would structure it a little bit different. But as today it's more about hydrogen technologies and what we can do in thermal analysis, I want to go through what's possible and where the research is going on, and then mention which kind of instrument comes into account at what stage of the hydrogen cycle we will see in the next slides. Therefore, I would just want to show you the overview of products. So we have DSC instruments, we have the classical thermal gravimetric instruments, and the simultaneous classical thermal analyzers, the combination of DSC and thermal gravimetric analyzer. Besides that, we have a lot of different dilatometers for thermal expansion and shrinkage, as well as sintering studies and thermomechanical analyzers for deforming measurements, for expansion and shrinkage measurements as well. And then, as I mentioned, we have instruments for thermal conductivity, which can be flash techniques, which can be hot wire and guarded heater techniques. We have thin film analyzers. We have thermoelectrical analyzers for microfilms, for thin films, for electrical effects like Seebeck effect, charge carrier concentration, Hall effect. And we do a lot of customization of all these products. That means we can adjust the temperature range, the pressure range, the exact sample size, depending on the customer's application. We also do evolved gas analysis. That means we can couple any instrument to a FTIR instrument or to a mass spectrometer or GCMS to get more information about the products that come out during decomposition. And we also can do a lot of high pressure and low pressure applications, which is also sometimes of interest, especially if you do catalyst research, decomposition research, coal gasification, and many more. Today's topic, back to the topic, the hydrogen and thermal analysis is something that plays a big role at the moment as Germany as well as Central Europe tries to get rid of fossil fuels, get rid of coal, get rid of gas, and tries to be more independent regarding energy. Therefore, there's a lot of research going on, and wherever research is going on, of course, laboratory equipment is also of interest, and that's why thermal analysis is strong in hydrogen technologies and is focusing on hydrogen technologies a little bit. As said, I will structure this talk today a little bit different than I would usually do. I will start with the hydrogen roadmap. So the complete topic and the complete structure of the talk will be along this cycle. The Fraunhofer research facility here in Germany, which is quite famous and involved in many, many research topics, they did a so-called roadmap and a plan regarding hydrogen, how it should look like and where the research is going and what's the goal more or less. And I think this structure is quite useful to explain where the research is going on, what they do, and I can show you quite easily where thermal analysis gets involved at this cycle. The idea is to replace energy that we have, like coal plants or gas power plants, even nuclear power plants, by renewable so-called green energy resources. That means photovoltaic, windmills, biomass power plants that should provide energy. Then the energy shall be transferred by electrolysis or other methods into hydrogen, and the hydrogen is more or less the energy carrier. It can then be stored, exported, be used as a fuel or in engines or in technical use. Even domestic use would be possible. And by using it, it will be transferred back into water. It goes back to electrolysis, and so you have a cycle. And I will go through the steps and show you what's the actual research, what's state of the art, and where we are already involved. So the key steps would be production of hydrogen, storage of hydrogen, and transport. So that's how I will structure this. The Fraunhofer Research Facility also did this overview about hydrogen research in the near future. I just summarized this a little bit and to show you where the research topics really are. So there's a lot of research regarding the electrolysis, the creation of hydrogen out of energy, and there's research regarding storage, of course, platform technologies, production rates should be optimized, the energy transfer rate should be optimized. Of course, there are catalysts that should be used, and so on. Besides that, the industry does a lot of transfer technologies. They try to replace hydrogen wherever methane gas or other fossil fuels are used directly, for instance, in steel production. They want to make methane pyrolysis. They want to make ammonia as an engine fuel because ammonia can be a chemical storage way for hydrogen again. They develop high volume storage capacities and many more. So that's what the industry does as well. And then there's the traffic and mobility sector, because hydrogen storage for mobility is something different than hydrogen storage in technical or power plant use. The on-site hydrogen generation plays a role when it's coming to mobility. So there's a lot of research. There's cooling techniques for mobile storage. There's optimization of the fuel cells themselves, which I will show you. And the fuel cell production lines are also under research. And then the last topic will also be the power generation. So power storage in form of hydrogen is fine, but getting the power back is also, there are many ways. One is the fuel cell. Others would be direct burning of hydrogen or chemical reactions. Direct coupling with renewable energy concepts is of interest, and there are also on-site concepts. So that's what really the research topics are at the moment, just to summarize that a little bit. And now I will go through this step by step. As I mentioned, first of all, the idea is to replace fossil fuels, nuclear fuels, and power plants by so-called green energy. Green energy means energy that comes from the sun directly without any emission of carbon dioxide if possible, or if there is emission of carbon dioxide, then it should be so-called green biomass, so wood and not fossil biomass like coal or something else. The typical resources or the typical sources of power are windmills, solar panels like you see here on the picture. Besides that, there are also geothermal plants and biomass plants. As mentioned, the goals are mainly the reduction of carbon dioxide emission and becoming or getting an alternative to gas and oil use. When it comes to these kind of energy production facilities, of course, there's material research going on. I'm focusing a little bit on the windmills and the solar panels, which is where we have already customers. For instance, the windmill blades are usually made of light composite materials or light alloys because they should not have that much weight to more or less improve the amount of power they can produce, because if the wind has to move a very heavy blade, a lot of power of the wind is already gone just for moving it. If the blade is quite light, the lighter it is, the more power you can get. However, the material should be stable. It should be not much expanding or deforming if sun hits it, or if temperature changes, or if the strength of the wind changes. And therefore, these materials are undergoing quite a lot of research. I had a customer that manufactured composite materials, glass fiber materials, and composite materials for that kind of plates. And they had different mixtures, and the application was to measure the expansion, to measure transformation temperatures when it gets soft or when it bends, and when it transforms and when it changes its phase. And what we did was just expansion measurements. So we measured the expansion, and out of the linear expansion during linear heating with 5 Kelvin per minute on a standard dilatometer, we found that at around 200 centigrades and at around 150 centigrades, there are two little phase transitions. You can hardly see them by pure eye if you just look at the absolute expansion, which is the green curve down here. And even if you look at the relative expansion, the red and orange curves in the middle, you see that there is a little bending and a little change in heating rate. And that means at that point, there is a little phase transition, a little change in behavior. If you take a look at the CTE, the coefficient of linear expansion, you see a definite change at the first phase transition and at the second. As that's a composite consisting of multiple different polymers, you know that one polymer has a glass transition here, the other one has the glass transition there. And out of that, you can imagine that at that temperatures, the blades will lose their structure, or the structure and the hardness of the blades could change, which is the information that these customers were interested in. They also saw that the one material has a slightly shifted glass transition and softening point than the other. So you see an effect from the composition on the mechanical structure and on the mechanical behavior of the material. And this is what you usually measure with that kind of instruments, just to give you an example where we are already involved in that topic. We also did measurements on the solar panels, not only expansion, but also thermal conductivity, which I did not show here and do not show here. But that's also already research that's ongoing, where we are already involved in this so-called hydrogen production cycle. As said, I want to focus on the main steps, not on the energy creation. So therefore, the next step would be the hydrogen cycle, the transformation from electrical to chemical energy. The idea is to create green energy by windmills, solar panels, and power plants, and then transform it into something you can store. You all know that electricity cannot be stored that easily. Of course, there are batteries. However, you need a lot of amount of material and matter to build a battery that can only save a little and very tiny amount of energy. They are improving and improving, but a battery that can feed a complete city or even a facility like production side of cars or whatever, that battery must be huge, really huge. And the state of the art is that you have to create the power as you need it. So you have to create electrical power on demand, or you have to store it somehow on a different way. One way, and the way of we are talking about today, is save it as hydrogen. The idea is using classical electrolysis, first of all, to create hydrogen out of energy. Therefore, it's quite easy. You have to transform your energy into DC. The DC is then brought onto the water by an anode and cathode that separates the water molecules into anions and cations. They are gathering at the anode and cathode and then forming hydrogen on the one side and oxygen on the other side. The oxygen can be released to the atmosphere easily as it's already there, and the hydrogen can be collected quite easily. And then you can use the hydrogen, store it, or do whatever you want. This is the classical process. Of course, that can be upscaled. On the picture down here, you see an upscaled electrolysis machine. which can create tons of hydrogen within hours when it's fed with energy. So it dissolves water into hydrogen, oxygen, technically. This is a pilot plant that's located in a small city not far from where we are located. So I was able to take the picture live and visit that, and it's quite interesting. This electrolysis process is also undergoing some research, and also there we have customers where we did already some measurements. It is, again, it's an expansion measurement. It's quite simple. These anodes and cathodes that they are using are usually made out of platinum, rhodium, and other alloys, and they are consumed over time. And what we did is, of course, they are doing research in more stable materials, and when they do that, they want to have mechanical properties. And if you upscale that and build a reactor like you saw on the slide before, and there are a lot of micro cells that do electrolysis, of course, they should not expand too much and shrink too much when heating, because during the process, of course, heat is created. And if you have a lot of small parts, the heat could be an issue if there would be too much deformation, too much expansion. Therefore, it's good to know the mechanical properties, and that's what we measured here. In that case, it's a quite simple measurement of one of these electrodes. It's just an expansion measurement to get the coefficient of thermal expansion and the relative expansion over a decent temperature range, to be sure that the material, if it's getting hot, that the material is not expanding too much, or if it's getting hot, how much it will expand, to be able to properly build your machine. So that's where we are already also involved, more or less. Besides the electrolysis, there is another way to create hydrogen when you want to create it out of biomass. If you have biomass like waste from food production, like waste from plant harvesting or something like that, or waste from animal farmings, you can use the biomass not only to fire it or to create methane gas and fire that. You can also use the biomass in a coal gasification or biomass gasification process to create more valuable gases like hydrogen, like sulfur, like methane, alcohols, and whatever. And the typical process is shown on the scheme down here. So usually it goes like that. You have coal, you have biomass or others. You feed them into a gasifier, and the gasifier simultaneously feed with oxygen and with water vapor. And then the water vapor reacts with your carbon, with the contained carbon of your biomass, and forms hydrogen and carbon monoxide. If you feed it with oxygen as well, it forms hydrogen and carbon dioxide. You can separate the gases that are created. You can use multiple filters, and out of that, you can get rid of sulfur. You can get rid of metals like quicksilver or other heavy metals like lead or whatever is contained in your material. And you can get clean syngas consisting of hydrogen and others. Out of that process, of course, you need energy for that. And this energy to heat your gasifier is what you can also get from green energy, from windmill power plants and so on. You can even use the hydrogen you get out of the process to feed that partially. And out of this process, as said, you can also transfer your biomass with use of green energy into hydrogen. That's another way that's possible. And this process is undergoing research since many, many years, because there are people who are trying to optimize that, to lower the temperature that's needed for gasification, to optimize the conditions of gasification. And that's where we have already a lot of experience, because we have a lot of customers who are buying our thermobalancers, who are buying our machines to simulate that gasification process. So what we have is a machine, a thermobalance, that can be operated under pressure, that can be operated in steam atmosphere. You feed it with a small amount of your carbon-containing sample. You heat it up in an atmosphere where you lose all your volatile parts, and then you start feeding it with water steam, leading to an immediate mass loss. So the red curve here indicates the mass loss. You have a lot of volatile, and once you're reaching your target temperature, you start feeding it with water, and you see the red curve decreasing. That means at that time, the carbon that's contained in your carbon-containing sample is gasified, forming carbon monoxide, forming hydrogen. If you couple this to a mass spectrometer, you can quantify the amount of gases that come out of your system, and then you can start playing around using catalysts, using pressure steps, using lower or higher amounts of water steam and so on to optimize that process. So this is one of our customer samples, and we have a lot of customers doing this. That's where we are already very much involved in this, more or less hydrogen generation technique. Of course, if you change the conditions and even more, feed in oxygen and so on, feed in more hydrogen, feed in more water, you can even find other gases like methanol, methane, and others, depending on how much energy, effort, and gas you want to spend. And that's where we are already involved so far. Going further in the cycle, coming to the hydrogen storage is one of the key parts. Because once you have created your hydrogen, of course, you now want to transport, you want to store, and you want to use it. Storing it is not so easy. And state of the art, or at the moment, there are 3 ways to store hydrogen. Short time storage is not an issue. Long time storage may be an issue, but anytime hydrogen storage is easier to achieve than electrical power can be stored. The 3 ways you usually can do it is either you use an adsorber, so you can do sorption studies, you can do sorption experiments, you can try to have a metal or metal mesh or other structures with micro or nanopores to do just sorption, so you can either controlled by temperature or controlled by pressure, you can adsorb it and release it. You can use classical gas bottles and just press it with pressure into a bottle, or you can do chemical storage by having it react with some other elements or other molecules to form a hydrogen containing molecule that can release it back again, either thermally controlled or pressure controlled or chemically by a catalyst controlled. And even there, we have partners that do a lot of research. Having a closer look at the sorption, the typical sorption or hydrogen sorption takes place at metalloorganic frameworks, which is a structure consisting of a metal grid with the organic surface, and the organic ligand or the organic molecules at the surface usually are responsible for forming pores within hydrogen can be located. And these MOFs or even zeolite structures, which is a ceramic structure also with little micro nanopores, they can all adsorb hydrogen by pressure and release it if the pressure is reduced, or they can adsorb hydrogen by temperature. If there's hydrogen presence and you lower the temperature, they will adsorb it. If you increase the temperature, the hydrogen will be released again. So that's what's going on regarding sorption. Besides that, as said, storing it in bottles is usually achieved by pressing it in there. The difficulty by storing hydrogen in bottles is if it's just pressed in there, there's always micro leakage because hydrogen is a very small molecule. It can diffuse out of anything. So these gas bottles will always have some micro leakages, and therefore they have to be placed and located outside of your building or in a room with a controlled air exchange. It has to be a vented room, and it's always a risk of burning, risk of fire, which is not so ideal. However, it's the easiest and most efficient way to store it at the moment. And besides that, there is also the possibility to do chemical storage, which is, in my opinion, safest way to handle it. If you have reacted with other molecules like nitrogen, you can form ammonia and use the ammonia as medium to store and transport it. You can adsorb it or making it react with some metals like titanium. Titanium can form a hydrate, which is more or less stable. There's no leakage, no hydrogen released if you do not lower the pressure and if you do not increase the temperature. And that's the chemical storage that's already going on. Of course, for all these, so mainly for chemical storage and for sorption, we have also partners and customers who are doing research using our high pressure balances again. What we can do here is simulate sorption and desorption process. So you can put in a sample, which can be an adsorber. You put it in, you increase the pressure, you lower the pressure, so you can feed it with hydrogen at higher pressure. Then you lower the temperature, you lower the pressure. You see how much weight is gained and how much weight is lost when changing the pressure, changing the temperature. And by that, you can measure sorption curves like in this application example. So in that case, that's a platinum aluminum catalyst with an active surface. And there was a little particle of 5.5 milligrams roundabout at 15 bar hydrogen. The hydrogen is applied, and you see there is a heat, a peak here, which is the heat absorption that was measured. You see that the sample is reacting, it releases some heat. At 80 centigrades, there is an exothermal reaction when the hydrogen is reacting with the surface. And what we also did, which is not, it comes on another slide, sorry for that. What's also done, what we did is we had a lot of adsorbers where we just measured the weight change. In that case, we already measured the heat absorption, which is also possible with a TGDSC instruments. Yes. Once you have stored the hydrogen and you have it available, you can use it wherever you want it. If you can control the sorption and desorption, if you can control the availability, you can use it as an energy carrier, you can use it as a fuel. In mobility, it's a little bit more difficult than if you have it in a power plant, because there you can have a big cell that sorbs it or desorbs it. In a tank of a truck or tank of a car, state of the art is a cooled tank with just a gas bottle or liquefied hydrogen. There's not much sorption and desorption going on in a vehicle. However, that may be the future as well. In a mobile engine, usually the hydrogen is used not by burning it like in a conventional engine. In case of a hydrogen-driven car or hydrogen-driven vehicle, usually there is a fuel cell. Fuel cell is one of the hottest topics regarding hydrogen research because it's the inversion of the electrolysis. A fuel cell has the job to transform hydrogen and oxygen back into water, providing the energy that you use to form hydrogen, giving you the energy back as electricity. That is achieved by this complex structure that consists of two chambers, more or less. One chamber is fed with hydrogen gas, the other one is fed with oxygen. And in the middle of the chamber, there's a membrane. This membrane is, can be passed by the small hydrogen molecules, but not by oxygen or anything else. So oxygen is hitting the one surface, hydrogen is coming from the other side, going through this membrane, hitting this membrane from the other side. And then there's an electrochemical reaction taking place. The hydrogen is reacting with the oxygen that's waiting here. And doing this, it releases electrons. The electrons are conducted through this electrical setup here. So the electrons are flowing over the membrane, going into your machine, providing electricity, and the water is dropping out at the exhaust down here. This is a controlled reaction between hydrogen and oxygen. It's not just burning off, it's really a controlled surface-bound reaction, providing a very high amount of energy out of that. Almost all the energy can be taken out of that. It's a quite known process and a quite optimized process. On the video over here, you see how the typical setup of a fuel cell looks like. And these fuel cells are already used in hydrogen-driven trucks, hydrogen-driven buses, and so on. There's not only one fuel cell that's fed by hydrogen and oxygen. Depending on the used membrane and the used gases, you can also feed it with other stuff like methanol, methane gas, hydrogen, of course, and you can make them react all with oxygen. And instead of burning them off, you can use a fuel cell with a decent membrane and get electricity out of the reaction instead of burning your gas just with oxygen. The idea is to cover multiple applications, to cover different temperature range. So these are just an overview of already commercial available fuel cells. They have different electrolytes in there. They have different membrane materials. Usually they have polymers, some potassium polymers, some phosphoric acids, molten carbonates, solid oxides, whatever, can be fed with different fuels and all have different temperature ranges. And of course, as this is a complex structure, we are involved in investigating these membrane materials. We're doing a lot of thin film analysis on that, measuring thermal conductivity, how much the heat that you get during the process has an influence on that, doing thermal stability tests, and doing also aging experiments with these membrane particles with our thin film analyzers to measure how long they last under certain conditions and when aging takes place and when not. yeah, that we have another example here, which is desorption. That's what I was missing 2 slides ago. So this is a controlled hydrogen released by temperature when that was a hydrogen that was adsorbed in a titanium matrix. And as you can see, you can desorb hydrogen temperature controlled in a 2-step process from this titanium surface, making a constant hydrogen release possible. And if you have a constant hydrogen release, then you have a constant possibility to feed something like a fuel cell. That was also measured by a thermal balance, as you see here. And that was the slide that I was missing 2 slides ago. I'm sorry for the for the mix up here. And once you have this controlled release, you can set, you can feed the fuel cell and anything like that. Another way where hydrogen is used instead of fuel use, you can use your hydrogen directly in technical processes. We have a lot of customers who are investigating ceramics and powder metals, and they do powder metal sintering and ceramic sintering. And very frequently, they are asking us to do sintering with a dilatometer or sintering with a thermomechanical analyzer in hydrogen atmosphere. Because during the sinter process, what you usually have is you have metals and metal oxides, and if you burn them in air, they will form an alloy, but they will sometimes also form alloy with oxides. And especially if you have sinter metals or special ceramics for industrial use, the oxides are not wanted. You want to have a pure metal structure, and therefore usually the oxygen is removed by the hydrogen atmosphere. So if you burn them and fire them in hydrogen atmosphere, you get a different result than firing them in air. And that's just also some example where we are already involved. So hydrogen sintering is something we typically do. A typical sinter curve and typical sinter process looks like this. The green curve down here shows your heating. So you heat your sample to a first target temperature where all your volatiles and all your humidity is evaporating. Then you have a little holding time, and after that you have a heating to your sinter temperature. During that really heating step to high temperature, the materials, your metals, your raw ceramics start to burn. They start to react with each other. They start to get rid of carbon dioxide, carbon monoxide, and so on. And they form your final product. You heat them up with a certain speed, and then you get to a target temperature that can be specified depending on the material. And then you hold the temperature until the plateau of shrinkage is reached. That means the sinter process is over when the plateau is reached and the sample is no longer changing its dimensions. Once this is achieved, you can start a defined cooling or ballistic cooling process. And during cooling, of course, your final ceramic will shrink naturally as every material shrinks when cooled or when being cooled. And this is a typical sinter process. In that case, it was a hydrogen sinter process of some catalyst materials, which we are frequently doing where we are already involved. Therefore, we have a special dilatometer that works under hydrogen atmosphere. So far about the use, I just want to mention that another kind of use of hydrogen in technical process is what we are actually doing research also, but I cannot show you the results so far is we have a customer who's replacing hydrogen in a steel production. Usually in steel production, you have a furnace that's fired with methane gas and classical fossil gases, and they try to replace the methane gas by hydrogen. However, if you flame methane, you get a lot of carbon monoxide, carbon dioxide, and water. If you burn off hydrogen directly, you get water. And the big amount of water in your technical process can affect your final product. So they investigate, on the one hand, the products in hydrogen atmosphere, as well as the firing process itself using our thermal balancers and meters in hydrogen atmospheres to be able to transform the steel production from use of methane to steel production when using hydrogen. That's also a very interesting project we are working on, where I cannot show you curves so far because that's already ongoing research. I just want to mention that. Coming to an end, after going through this hydrogen cycle, I want to show you one important thing that I have to mention here at that point. I showed you our product range at the very beginning of the talk, and I mentioned that almost every kind of instrument we have can be operated in hydrogen. Of course, we have to modify it a little bit. We have to use hydrogen tight sealings. We have to make sure there's no leakage and so on, but they can operate in hydrogen atmosphere. What we indeed recommend and do is to add a hydrogen safety unit. Therefore, we have our own unit available that can be coupled to any of our instruments. And this hydrogen safety unit is highly recommended when using thermal analysis instruments or any lab instruments at all in hydrogen atmosphere or in any flammable atmosphere. And I want to introduce to you, before I finish the talk, this hydrogen safety unit a little bit. As said, all our instruments can equip with that, and this unit, well, how it works and what it does, it's a completely automated gas control, first of all. So it automatically can control the evacuation of your instrument and the filling with inert gas and of course with reactive gas. So this instrument is connected to a vacuum pump that evacuates your system, fills it with inert gas, evacuates again, fills it with reactive gas, which may be hydrogen, with maybe anything else. Of course, you can also start an experiment at inert gas, heat it to a certain temperature, and then bring in the hydrogen or reactive gas, which can also be controlled by the automatic gas control here. It has an integrated burn-off unit with 2 igniters, so the outgassings that come back out of your instrument are also controlled, and they are flamed through a burning standing flame with 2 independent igniters to make sure there is no flammable gas released to the room. It has automatic mass flow controllers. They are monitoring the flow rates. They are monitoring the pressure within this mixing unit. They are monitoring the pressure in your instrument. They can detect gas flow blockage. So you can, in case of the outlet is blocked somehow or the inlet is somehow blocked, they can detect it, and it can operate independently from PC. So even if there is a PC issue or USB issue, this safety unit will still work. In case it detects any leakage of hydrogen, it detects any gas flow issue, it will automatically bring your system to a safe state. It will flush the system with inert gas and therefore make sure that nothing can happen. What it does in detail, and you see it here coupled to an STA system, you have a sensor array in the system, and this sensor array is connected to gas sensors around your system, within your system, and in the environment. So you can monitor hydrogen leakage in the system, at the system, around the system, and in the room. And once these sensors detect the hydrogen leak, or there is an empty gas cylinder, even if it's the inert gas cylinder, or if the inert gas is below the threshold, the system will stop the hydrogen flow, close the bottle, will flush your system, bring it to a safe temperature, bring it to a safe state, no matter what happens. In case of a burner is failing, there is a power outage, or the furnace is cooled down too quickly and there is a risk of no sufficient overpressure, this automated control system makes sure there is no risk when operating with this complete setup. If the system brings the system to a safe state, it purges with inert gas for 3 minutes, around 10 times the chamber volume, to get rid of the hydrogen in there. So you can open your system anytime it cooled down on a safe state, and there's no risk of releasing hydrogen, causing explosions, burns, and whatever. So that's what we do, what we can handle quite well, and that's what we offer with our systems, just to introduce that to you. Of course, one final word about safety. The hydrogen safety system is only one step. We also have an integrated timer. If you use one of our systems in flammable gases, it monitors the working hours and recommends a service interval when you should do a maintenance. And during the maintenance, the inner tubings, ceilings, and fittings are checked, thickness is measured, and surfaces are controlled to make sure that there's no little crack, no risk of breaking during operation, and so on. And of course, we use special hydrogen ceilings that should be replaced during maintenance as well. And as said, there is an integrated timer and that monitors the working temperatures and hours and gives you a hint when maintenance is necessary. And doing this, we are able to be or to operate all our systems be operated in hydrogen atmosphere. One final thing is, if anybody of you who's interested in that kind of instruments has further improvements or sees something that we might be missing or might be able to improve, we are already open and will be always open for improvements, for suggestions, for ideas, because that's a topic that we are already interested in and where we get a lot of requests in the recent past. And therefore, if anybody has improvements, we are always open for emails and for visits and so on. So far about the hydrogen topic. As said, this talk was a little bit different from the other webinars where we just introduce an instrument to you. This is more or less an overview of hydrogen research and where we are already involved. just to show you that this is a topic we are very much interested in and we are willing to do cooperations in the future. I want to thank you for your attention and thank you for your time spending with me.